Hey everyone, we're going to get started with the second session. So, welcome. I'm Daniel Neal. I am the session moderator. I'm from New York University. I also spent 15 years at Carnegie Mellon, so I'm really delighted to be back here. So we've got 4 great talks this session. As usual, they're going to be 12 minutes plus 3 for questions. I'll be sitting there keeping time, giving people notices at 2 and 1 minute. So our first speaker here, come on up. Hey, wonderful. All right, so our first speaker is Ali Shirali. The talk is The Hidden Cost of Waiting for Accurate Predictions. Ali?
Thank you. Okay, hi everyone. I'm Ali, and I'm going to talk about the hidden cost of waiting for accurate predictions. So let's get started. I hope that we all agree predictive systems are nowadays widely used to efficiently target individuals and allocate resources. And those resources might be, educational resources or homelessness funds, and many more examples. There is a hidden common assumptions in all of those applications, which is that if we improve our predictor, we are going to likely have a better targeting or allocation. And this is something which I'm going to look into today using a dynamic stylized model. But before that, I would like to give you some intuition by walking you through a working example. And let's look at that. So suppose that we have a planner who tries to prevent some poor outcomes. Those might be evictions, or school dropouts. And then we also have some resources to prevent such outcomes. Those might be housing watchers or tutors. Then we have some individuals who differ in how much they benefit from these resources. We also assume that each individual can receive only 1 unit of resource and only once. With that, then if we knew actually those, we assume that there exists a ground truth priority or ranking over individuals. And if we knew that ground truth ranking, the problem was kind of easy. We just had to sort the individuals and allocate the resources to the people with the highest priority. But that's not often the case. So what's a viable solution here? We can obtain maybe an individual level risk predictor like the red bars here, and then prioritize based on this individual predicted risk. All right, so the assumption here is probably that if we obtain a better predictor, we're going to have a more efficient allocation. And that kind of makes sense because if in this figure, if I kind of improve those red bars, eventually I'm going to recover the ground truth ranking and my allocation becomes optimal. So how can we improve that predictor? If we are working with the same pool of individuals, maybe we can just wait and collect more information from them, which leads to this conclusion that maybe it's a good idea to actually wait and collect some information before acting on individuals. As you may guess, this is not a complete picture because those predictions were means for something. We wanted to prevent some poor outcomes. And although this is true that more accurate predictions probably give us, a better identifications of the individuals in need, but we might also lose some vulnerable individuals who would actually benefit from some early interventions. So there is a trade-off here, which I'm going to formalize. All right. So before looking into the model, I wanna say 2 things. I think whenever we make that decision to whether we want to improve the predictor or not, we have to answer 2 questions. First of all, at what cost I'm going to improve my predictor? Here, we're going to have a cost of opportunity to act early. In prior works, we have looked into the cost of more restricted access, because if you're spending money to improve your predictor, you could probably you're losing some money to do something else. This is something which my colleague has looked into. Also, generally, we should also sometimes ask, do we actually need a fine-grained predictor or not? Which is something which I have done in one of my prior work. But in general, I think we should always ask at what cost we are actually obtaining this predictor. The other thing which we need to answer is that in what means we are improving that predictor. Is it going to be a better accuracy, better calibration, or something else? In the stylized model, which I'm going to present, this question has a simple answer because I'm going to assume that we are using a Bayes optimal predictor, and the improvement only comes from making or observing more data from the users. But in general, I think that's a relevant question that we need to ask. Okay, these are the things which we need to think about. Now let's look at the model, which I'm going to use to answer, the initial question of when waiting for more observations is actually helpful. Okay, we have an individual I. I'm going to assume that every individual has some sort of inherent failure probability pi, which is not going to change over time. So going from t to t plus 1, the individual is going to fail with probability pi. Then if we treat that individual, we're going to observe an effect of size tau, which depends on the individual, of course, and the time, and of course, the failure probability of the individual. I'm going to make an assumption that tau is increasing in P, which means if the individual is more likely to fail, they're going to benefit more from that intervention. Also, it's decreasing in T, which means that if you're going to allocate something to the same person, they're going to mostly benefit if we do it earlier than later. On the planner side, the planner has a fixed budget. They have to allocate that until some horizon T, and they want to maximize the sum of the treatment effects on those individuals who are treated. So that's the problem. Again, if we knew those inherent failure probabilities, the problem was simple. We just had to sort failure probabilities and allocate to those which have the largest values of P. But that's not often the case. We don't observe those failure probabilities. Instead, we're going to assume that we have some binary signals from every individual. So at every time point, an individual is going to emit a signal. The mean of that signal is going to be increasing with their failure probability. An example would be that this signal is just whether a student failed an exam or not. And monotonicity here means that if an individual is more likely to drop out, they're also going to be more likely to fail an exam. So that's a kind of natural assumption here. All right, so I'm going to look into this problem. This is an allocation problem based on some predictions. But before that, I think just forget the allocation part. We have a dynamic and we have some signal. I think we can ask a more fundamental question, which is, if we look at the planner's ranking over individual, would that ranking even be improved over time or not? And this might seem to have a trivial answer, but it doesn't, because we are making predictions and ranking individuals who are changing. The pool of active individuals is actually changing over time. That's why this question has a non-trivial answer. After answering that, I will get quickly through the allocation part, and I'm going to look into two instances. The first one is a one-time allocation, when the planner has to allocate all the resources all at once. And the second one is the overtime allocation, where the planner can spend the budget at every time point. All right, let's look at the ranking part. What I'm gonna do is that we're gonna look at the pairwise ranking risk of an optimal ranker. And then we're going to see if this ranking risk how is this ranking risk changing over time. So if we look at the ranking risk change over one time step, we're going to see that it's going to change proportional to this, which I'm going to explain. First, there are some negative terms which show that the ranking is being improved. Those are very familiar terms in statistical learning. But there is also a positive term which tells us that the ranking might get worse. And this is what we call a change in population effect. And it exists because the population is changing. It's just getting harder and harder over time to rank those individuals, because probably those who were easy to rank are already dropped out. Another interesting observation here is that this change in population effect is actually proportional to the variance, which I interpret as the inequality. So higher inequality means that it's more likely that the ranking gets worse sooner. So that's about the ranking. Now let's look at the one-time allocation. Here we need to answer this question: when is the best time for the planner to act? And for this short talk, we have the general case in the paper, but here I'm just going to assume that we have fully effective treatment, which means that if we intervene on someone, they're going to survive until the last time point. So the math really doesn't matter here. And we make an interesting observation here, which is there exists a critical time point after which the planner definitely should have spent all the budget or should have intervened earlier than that. So the existence of such a critical time point is interesting. Even more interestingly, this critical time point depends on a few parameters. The first one is the parameter G, which is a function of the probability distribution of failure probabilities. I'm not going to define it, but intuitively that's related to variance. And a lower G means a higher inequality. There's another term, which is the budget. So we can see a higher budget means you have to act earlier. And as I just explained, a higher inequality also means that you have to act earlier, kind of consistent with the previous observation. So that's about the one-time allocation. There's also an overtime allocation where we ask, how should the planner allocate resources over time? This is a hard problem if you want to solve it naively. It can be exponential in the number of individuals and the budget that you have. But luckily, this optimal solution has some structure which allows us to propose an algorithm to actually simulate optimal overtime allocation. So we use that algorithm and simulate overtime allocation on a national education longitudinal study. And we look at how much of a budget should be spent at different grades or different time points of a student life at a school. And we see, for example, kind of consistent observations with the one-time allocation. If we increase the budget, most of the budget has to be spent earlier than later. Also, if we have a higher inequality, we should spend more of that budget earlier. So kind of consistent stuff. With that, okay, there are a lot of things which I'm going to leave for future work. For example, the signals might be noisier than I thought. And also collecting observations might be costly. Here they're coming free. So I think these are interesting extensions to this model, which might make it more realistic. Also, observations are quite simple here. They're just binary. They can be more complicated. I would like to conclude here and just say that waiting to gather more information is not always maybe a good idea. As we see, we always need to ask what's the cost of improving that predictor. Here we had some sort of opportunity cost. We had some characterization of when it is not preferred to actually wait for more observations. If you're looking at the ranking or one-time allocation, we also showed some empirical result. Then the same kind of trends holds when we look at the overtime allocation. And so I want to say that in general, I think that evaluating predictive systems for decision-making in societal context has some technical challenges because often there are some assumptions in machine learning models that do not hold there. And this is just one example here. And I really hope to see this community that we have kind of engages more deeply in this kind of questions. Yeah, that's it.
Okay, so we have time for, I think, one or two questions.
Okay.
Okay, there are people coming around with the mic. Any hands?
There's one person there.
Hi, thanks for the talk. It sounded like you only considered deterministic allocation rules. Is that true? And would things change if you considered also I don't know, weighted lotteries or something like that?
Good question. Yes, we had two instances of the allocation. The one-time allocation is certainly deterministic. The other one, it turns out that because we characterize the optimal allocation for the overtime allocation as well, and it turns out to be actually deterministic. So I don't know if there's any value to make that a stochastic or not. Yeah.
Thank you.
Okay.
I was going to ask right now, you have information that are independent across users. So if I learn something about a user, it's only for that user. And I was wondering if there's any extension where what you learn about someone may help you learn about another because of structure.
Okay. Yeah, I mean, I'm making this simplifying assumptions that, I'm kind of thinking about individuals independently and there's no grouping structure or whatever that might be also very important and realistic. This is not something I have thought about, but yeah, certainly an important aspect. Yeah.
Wonderful. Let's thank the speaker again.